Imagine two particles, born from a single event, flung across the vast expanse of the cosmos. These particles, though separated by light years, share a mysterious connection that transcends the physical space between them. They are separated by unimaginable distances, yet remain connected in a way that defies our classical intuition. This connection is not just a theoretical concept. It has been observed and measured in countless experiments. This is quantum entanglement, a phenomenon so bizarre, so counterintuitive, that it has the potential to shatter our understanding of reality itself. Imagine a dance where the partners are so in sync that even when separated by vast distances, their movements remain perfectly coordinated. At the heart of this enigma lies a profound question. What if time, as we perceive it, is but an illusion? What if our linear experience of past, present, and future is merely a construct of our limited perception? This isn't science fiction. This is the bleeding edge of theoretical physics, where quantum mechanics and general relativity collide in a maelstrom of mind-bending possibilities. Scientists are grappling with these concepts, trying to reconcile the seemingly irreconcilable, and at the center of this storm is the very fabric of our universe, space-time. This fabric is not just a passive backdrop, but an active player in the cosmic dance, warping and bending in response to the presence of mass and energy. Could it be that time, the river that seems to carry us all towards an unknown future, is not a fundamental aspect of reality, but rather an emergent property, a consequence of a deeper, more fundamental quantum reality? This idea challenges everything we think we know about the universe and our place within it. From the dawn of human consciousness, we have perceived time as a linear progression, an arrow flying unerringly from past to future. This perception has been deeply ingrained in our cultural and scientific narratives, shaping how we understand the world around us and our place within it. Newtonian physics, the cornerstone of our classical understanding of the universe, reinforced this view. According to Newton, time was a constant, an unchanging river flowing steadily onward, unaffected by the events occurring within it. Time in this framework is absolute, ticking away at a constant rate for all observers, regardless of their relative motion. This concept of absolute time provided a reliable foundation for the laws of motion and gravity that Newton formulated. It is the backdrop against which the grand cosmic drama unfolds, a stage upon which the laws of physics play out with predictable certainty. The stars, planets, and galaxies all dance to the rhythm of this universal clock, their movements governed by the unyielding laws of classical mechanics. But this seemingly intuitive picture of time begins to crumble at the edges when we consider the universe on the grandest scales and the smallest. The predictable clockwork universe of Newtonian physics starts to falter under the scrutiny of modern scientific discoveries. Einstein's theory of relativity, a revolutionary framework that overthrew Newtonian physics, revealed that time is not absolute, but relative. This groundbreaking insight showed that time could stretch and compress, influenced by the presence of massive objects and the speed at which an observer is moving. Time, Einstein showed, is intertwined with space, forming a four-dimensional fabric called space-time. This fabric can be warped and curved by gravity, leading to phenomena such as time dilation, where time moves slower in stronger gravitational fields. The flow of time, once thought to be immutable, is now understood to be affected by gravity and motion. This new understanding has profound implications for our conception of the universe, challenging our deepest assumptions about the nature of reality itself. Quantum mechanics, the other pillar of modern physics, introduced an even more radical concept, entanglement. This phenomenon, famously dubbed spooky action at a distance by a skeptical Albert Einstein, describes a peculiar connection between two or more quantum particles. Once entangled, these particles remain linked, no matter how far apart they may be. Measuring the state of one particle instantaneously determines the state of the other, even if they are separated by billions of light years. This instantaneous correlation, defying the limitations of speed of light, posed a profound challenge to our understanding of causality and locality. How could two particles communicate faster than light, seemingly violating one of the fundamental tenets of Einstein's own theory of relativity? This question has puzzled physicists for decades and remains a source of intense debate and research. Section 4. The Page and Wooters Theory. Time as an emergent phenomenon. In the 1980s, physicists Don Page and William Wooters proposed a radical solution to the entanglement puzzle. Their groundbreaking theory challenged the conventional understanding of time and quantum mechanics. They suggested that entanglement doesn't actually involve faster than light communication, because time itself is an emergent phenomenon. This idea was revolutionary, as it implied that our perception of time might be an illusion created by the quantum world. In their framework, time is not a fundamental aspect of reality, but rather a consequence of entanglement. This means that what we experience as the flow of time is actually a byproduct of the quantum states of particles becoming entangled. They argued that the entangled particles aren't communicating at all. Instead, they are part of a larger interconnected quantum system where time emerges from the relationships between particles. Instead, they are both part of a single, timeless quantum state. This state encompasses all particles and their interactions, creating a unified field where time as we know it does not exist. Imagine a deck of cards, each card representing a different point in time. Now shuffle the deck. The cards are now in a random order, but each card still exists, representing a moment in time. The order of the cards is now random, but each card still exists. This analogy helps us understand how all moments in time can exist simultaneously, even if we perceive them in a specific sequence. In the same way, Page and Wooters proposed that all moments in time exist simultaneously in a superposition of states. This superposition means that every possible moment is real, but we only experience one sequence due to our observation. It is only through the act of observation, through our interaction with the quantum world, that a particular sequence of events, a particular timeline, emerges. This interaction collapses the superposition into a single, observable reality, giving us the experience of time. Section 5. Redefining reality. The implications of quantum time. If the Page and Wooters theory is correct, our understanding of reality needs a radical overhaul. Time, as we experience it, would be an illusion, a construct of our conscious perception. The past and the future would exist simultaneously with the present, all entangled in a cosmic dance of quantum possibilities. This has profound implications for our understanding of causality, free will, and even the nature of reality itself. If the future already exists in some sense, Is free will just an illusion? Are we merely actors playing out a predetermined script? Or do we have the agency to choose our own paths, even within the constraints of a pre-existing quantum landscape? These are not just philosophical questions. They are deeply intertwined with the fundamental nature of the universe and our place within it.